Hi everyone, and welcome to our P4 review. So the goal of tonight then is to go through the topics that we will need to know for the P4 assessment that's going to happen in class tomorrow. Now this is for the Triple Science P4, which is all about magnets and magnetism. So, as always, we've got the chat window running there so that if you actually need anything answered, then by all means, feel free, ask in the chat window and I'll do my best to answer it as we go along. We do always get a little bit of a slight delay between these, so bear with me if it takes me a little bit to get back to that question. So, the start of P4 then, we kick off with looking at magnets and magnetic fields. And what we do is we start off by going back to the real basics of the work that we did all the way back in Key Stage 3. So we have the idea of those two bar magnets, and if we place them together, then we will get different interactions depending on which poles of the magnets face each other. So if we have a north pole facing a north pole, then they repel. If we've got a south pole facing a south pole, they repel. And if we've got a north pole facing a south pole, they attract. So what we see there are the two key things we need to remember about magnets. Like poles will repel, so two of the same will repel, whereas opposite poles will attract. So a north and a south will always attract each other. When we actually did this lesson, then what we did was we had our little bar magnets usually, and we'd sprinkle iron filings over them in order to have a little look and see what the field lines actually look like. And the reason we do that is because by sprinkling the iron filings on there, we can actually see those field lines which represent the magnetic flux. Now, when we've done that, we can actually, just by looking at the actual arrangement of the iron filings, we can work out the strength of that magnetic field, purely by how many field lines pass through a particular area. Because if we've got a lot of field lines, then that has a high magnetic field strength or a high magnetic flux density. Whereas if there's only a very small number of field lines, then it's a low magnetic flux strength or a low magnetic flux density. What we do find is that if we've got two magnets, then what we have are two competing magnetic fields. So because we would hold them close together initially, then we've got obviously the two different bar magnets, their field lines are going to interact. And they're going to actually move the magnets in whichever direction would make the field lines as short as possible. So when we've got a north pole here and a south pole here, it pulls them together because that shortens them as much as possible. Whereas the north pole to the north pole, if you actually leave those magnets, what happens is, and you take your hand away, it's going to spin all the way around to face the other way and then attract, because you'll have the south pole facing the north. The whole thing there is to do with shortening those field lines. Now, we have two types of magnet we need to know about. The permanent magnet, first of all, which is one that is always magnetic, even when other magnets or the current is removed. And then the induced magnet is just a magnet which is only produced when a magnetic material is placed in a magnetic field. So that if we were to remove that magnetic material from the magnetic field, it may or may not stay magnetic. So this would be an example of just putting a little bit of metal within our magnetic field. It would be a magnet for that short period of time, take it out, loses its magnetic ability. So permanent magnets, always magnetic. Induced magnets, only when they're in the magnetic field. The way we can actually explain those properties is in something called the domain model of magnetism. So quite simply, this just tells us that a permanent magnet is made up of many small magnetic regions called domains, which are all perfectly lined up. So your permanent magnet, those domains are all nicely in alignment, hence it is magnetic. If we think about a metal such as iron or steel, these have those domains, but they're all in different orientations, so they're not lined up. If we then place that piece of iron or steel into a magnetic field, those domains do line up, and therefore it becomes magnetic. When we take it out, the domains may go back to their original orientations, no longer in alignment, and it won't be magnetic anymore. So what we have are the two different regions or reasons that we've got our magnets there. Permanent magnet would just be a bar magnet because that is always magnetic whether we placed it into another magnetic field or not. And an induced magnet, quite simply a piece of iron, because it's not magnetic normally, but if you place it into a magnetic field, it will become magnetic. The next device which we'll look at, which is incredibly useful to us in terms of navigation, is a compass. Now, this isn't the one on your phones, this is actually the good old-fashioned compass with the point that spins around. Now, compasses will point towards the magnetic North Pole. Do not confuse the magnetic North Pole with the actual North Pole on Earth. They're close, but not exactly the same place. And what we actually find is the reason that we can use a compass is because inside the actual structure of the Earth itself, we've actually got a whole load of iron. Now, that's mainly within our core particularly, and because we've got these different fields that occur within our core and different currents, we generate this giant magnetic field around our planet. So what we actually have is something to the equivalent of having a giant bar magnet at the centre of our Earth. Now, the reason for this is that within our core we've got these areas where some bits are hotter than others, and that causes convection currents. So hopefully we remember convection in terms of our energy, so that what we find is when things are warmer, then they tend to rise because they're less dense, and then as they cool, they become more dense and sink down. So you get this kind of flow that goes around. And this happens within the core of our Earth, and that's going to be molten iron that's moving around doing this. And as it does so, it generates this magnetic field, which then the compass point will respond to. So that's our quick overview on just the magnets first of all. Hopefully nothing too revolutionary there. They could ask you questions on the exam about the experiments, either to do with plotting those magnetic fields using the little tiny plotting compasses or using iron filings. The method is pretty similar. So you start off with your bar magnet, and then you're going to place your little plotting compass near to it first of all and mark the direction it points. You then move the compass, do the same thing again, move the compass, do the same thing again, and then you can join those little dots to actually show the overall field lines. If we're doing it with iron filings, you place your bar magnet down, you put a bit of paper or card over the top of it, and then you sprinkle the iron filings over the top. They will then align in the shape of those magnetic fields. The only other question that I've seen in relation to that, as far as I can remember, is asking why, as a teacher, that we may prefer the compass method rather than the iron filing method. And the simple answer is, it's less messy. If you lot all get iron filings and start shaking them all over the place, then iron filings go everywhere. That's a nightmare. They stick to the bar magnet, they get on the floor. No. Little plotting compasses, far easier. Obviously, one way that we could avoid the mess is by placing the actual bar magnet into a plastic bag before we use the iron filings, so you could include that in your method if you wished. So, next bit is looking at a piece of wire. If we have a single length of wire and we connect it into a circuit so that a current is going to flow through that single piece of wire, we will generate a magnetic field around it. Because any current carrying wire will also have a magnetic field. If it's literally one piece of wire and we want to know the shape of that magnetic field, it's just circles, one inside the other, concentric circles. So it just means that we've got one circle and then another one inside it, another one inside that, and so on, getting smaller and smaller and smaller. So what we actually have here then is the shape of our magnetic field. But we need to know the direction of it as well. This is where our right hand comes into play. With a single piece of wire, straight wire, what you do is use your thumb, so it's good old thumbs up moment, and your thumb points the direction the current is flowing in. So if the current was flowing upwards, then we point our thumb upwards, and then if you look at the direction that your fingers curl in, that's the direction of your field. So you can then just put that arrow onto the circles. Obviously if it's flowing down, flip your fingers the other way up, and then you get the opposite direction there. Do remember that a single piece of wire, it's your right hand thumbs up. That's what we're going to do for this one. Now, what we actually find then is, again, this is an experiment they could ask you about. So you just need to talk about the fact that we take a piece of wire, connect it into a circuit, turn it on, obviously, and then we place the compass next to the wire, mark where it goes, move the compass, mark where it goes, and so on. The only thing I'll say here is do read the question carefully, because one of the ways that people fall down is they start answering about the bar magnet experiment when it's actually asking you about a current carrying wire, or vice versa. So just make sure you know, are you talking about a wire or a bar magnet, and then talk about the right one. You do actually have a little bit about the magnetic flux density or the magnetic flux strength that you need to know about. And this is just looking to see what it actually depends on. And the thing is, there's only two factors here that will affect it. The first is the magnitude of the current. So the larger the current flowing through that wire, then the stronger the magnetic flux density will be. And the distance from the wire as well. So that the closer we are to the actual wire, the stronger the magnetic flux density. So just remember those two patterns. Magnitude of the current, the bigger it is, the stronger it is, and the distance from the wire, the closer it is, the stronger it is. The units for magnetic field strength is Teslas, which is a capital T. Just make sure you remember that bit. Now, we also need to take this a little bit further to the current flowing through a loop of wire. And if we've got this, then what we find is we'll have our concentric circles on either side where the loop goes through our bit of card. But between those two circles, we actually just have a straight line. So just remember there is that straight line that runs through the center there. If we go one step further, we can talk about solenoids. Now, a solenoid is just a coil of wire. And the reason that we actually care about solenoids is because this is a way that we can actually make a much stronger magnetic field. So the more loops of wire we've got, then the stronger the magnetic field we generate will be. And this allows us to make some pretty powerful magnets. If we wanted to make it even stronger, we could actually just slide a magnetic material like a piece of iron or a piece of steel into the middle of that coil, and then that would make it even stronger. So what we then have is the ability to create an induced magnet in that iron core when the current is actually flowing through it. Now, the whole purpose behind this, as I've said, we can make these strong magnets, these things called electromagnets. And you may have heard about these in terms of those like car scrapyards where they want to lift a car and they've basically got that big thing that comes down, just sticks to the roof of the car and lifts the whole thing up. That's an electromagnet. We also use electromagnets in MRI scanners in medicine. So that's the device where they might want to look at bits inside your body. They basically get you to lie on this table that then just goes into a big tube, and you then have this lovely, very noisy sound as they then scan you with very powerful magnets. Before you go in there, they will ask you to remove any metal because otherwise the MRI scanner will do it for you. Not good if it's earrings. So, next thing we need to come on to is thinking about what happens when we've got more than one of these magnetic fields. So this is where we're starting to now look to see the interactions of these fields. So if we've got our current carrying wire, we know that it has a magnetic field around it. If we place that current carrying wire inside another magnetic field, then those two magnetic fields are going to interact with each other. And basically what they do is they push on each other, and that creates a force on the wire which makes it move. And the force on that wire is always at right angles to the magnetic field itself. So what we have is this movement of the wire as a result of the magnetic field we have generated. Now, we generally cause something called a catapult field here. So when we've got our wire, the lines get stretched in our magnetic field. Now that means that they're not their shortest possible length, so what happens is they're going to actually push the wire downwards in order to shorten. So that moves the wire in one particular direction. The way we work out what direction it moves is Fleming's left-hand rule. So left hand's at the ready. Hopefully we do know the difference between our left and our right hand. And what we actually need to do here then is, remember, we have 3 fingers that are important, 2 fingers and a thumb. So first of all, your thumb is going to be the movement, your first finger is going to be the field, so the magnetic field, and then our third finger here, okay, the second one, this is going to be our current. So this is where we do our kind of dodgy little hand signal here. We start off finger guns, okay, always the easiest thing to do. This is the easy, not uncomfortable part of this. Then we've got to remember to stick out the second finger. That's the less comfortable part. So we end up with that kind of system. This is how we know what direction any wire moves. What we do first of all then, with our lovely finger gun, is you're going to line it up with facing from north to south. Right, let's see if we can actually do this on our little picture here. So this is a picture of the kind of thing we could get. So we've got north is here and south is here. So the first thing we're going to do, and this is going to be awkward, is, oh, hang on, let me just angle my hand there. We point from north to south with our first finger, okay? Then our second finger is going to have to point in the direction of the current, and in this case, it's going into the paper. So this one, try and get my hand upside down. Imagine I turn my hand upside down. I can't do it with a bit of paper there. But we need our second finger to be pointing into the paper, which means that our thumb is then going to be pointing downwards. So we get that downward motion of the actual wire. This is what we need to do, okay? North to south. Your second finger here is always going to point in the direction the current flows. Now, when they give you the diagrams, it's either going to be into the piece of paper or out of the piece of paper. So the direction that that wire will move will either be up or down. Should be quite simple to work out from that bit. The best thing I can suggest is practice with Fleming's left-hand rule, because trying to do this in an exam for the first time, number one, you're going to look pretty strange when you're trying to work out which fingers you need to stick up and in what directions. And secondly, you need to get used to kind of flipping your hand between those different directions in order to actually match the picture you've got on the bit of paper. The next bit we've actually got is a calculation, but the good news, it's not actually one you've got to memorise. Finally, we have a formula they're going to give you on the physics formula sheet. There aren't many these days, but when they occur, we are very pleased. And the formula that you will get is that the force on a conductor carrying a current in newtons is the magnetic flux density in Teslas times the current times the length. Length is in meters and your current is in amps. So what we find here then is that the size of the force is going to depend on those three things: the current, the length, and the magnetic flux density. As I say, that formula is given to you on your formula sheet, so you've just got to be able to use it. The way they make this a bit trickier is that they're not going to give you the length in meters, they're going to put it in centimeters. So to convert centimeters to meters, all you've got to do is divide by 100. They could also give you the current in milliamps rather than amps, but again, just convert by dividing by 1,000, okay? So what we can do there is just make sure you're looking at the units they give you in the question and make sure you convert to the standard units before plugging it into your calculator. And as always, with all science papers, you are allowed a calculator in every single exam, so make sure you use it. Don't try and do mental maths. It's a ridiculous risk at this point. Now, once we've got the basic idea of the fact that when we place a current carrying wire in a magnetic field, then it's going to move in one or two directions. What we can do is we can then build devices that use that. And the first device that we come onto that uses this is a motor. Because to all intents and purposes, a motor is a loop of wire within a magnetic field. And what's going to happen there is, if we look at our little diagram up here, we can see we've got our loop of wire within our magnetic field. So as the current flows, what we'll see is one side is going to move up and the other side moves down. Because obviously the current is going in on one side and out on the other. So that means we get the opposite motion on the two sides of the actual loop of wire there. Now that means it's going to turn. What we need to be able to do though is have a system where it can spin continuously. If we didn't have something to allow that, what would happen is it would go so far and then it would stop, okay, because it couldn't keep turning in that one direction, because otherwise the current is then going the other way, which means that the wire is going to be pushed back on itself. The way we solve that is by a little device called a split ring commutator. And a split ring commutator is this little thing here. As the name suggests, it's basically a ring with a split in it. Now, what we have here are the little brushes that connect onto the edge, and we've then got the coil of wire attached onto each of the two halves. Now, what's going to happen here is, as it spins, then this whole thing is going to turn as well. But because we've got those gaps, once it's gone through 90 degrees, the gaps are lined up with the connections to the circuit. No current will flow, just momentum keeps it going. And then as it reconnects, what happens is this side is now obviously the opposite charge. So that means what we end up with is our coil of wire will keep spinning in the one direction, because the force on the left is always in the same direction and the force on the right is always the same direction, even though the two halves of the coil of wire switch sides. So it just keeps it going all the time in a nice continuous fashion. One of their favourite questions to do with motors is they're going to ask you how to change the speed of it. Now, this should be quite an easy question, but again, it's the wording that you've got to go careful with. Because if they say, how can you change the speed of a motor? Then you can literally write down, change the size of the current, change the strength of the magnetic field, change the number of coils in the wire, change the length of the coil. If, however, they say, how can we increase the speed of the motor? Then what you'd have to say there is increase the size of the current, increase the strength of the magnetic field, increase the number of coils on the wire. So just look for that very subtle variation in the wording, because otherwise you can really easily throw the marks away. Because if they just ask you, how can you increase the speed of our motor, and you say change the size of the current, it's not going to get you the mark, because obviously change could either be an increase or a decrease. So just make sure that you are using the right terminology there. The next bit we come on to is one of the higher tier concepts, and this is all about electromagnetic induction. Now, the whole principle of this is that if we move a wire in a magnetic field, it's going to cut those field lines. When that happens, then we are going to induce a potential difference across the wire. So the basic premise is we have a piece of wire, it doesn't have a current flowing through it at this point, but if we move it through a magnetic field, therefore it's going to cut those field lines, it will have a potential difference induced or created across the wire itself. When you induce a potential difference, then we have a current that will flow. So what we've actually done is we've caused a current to flow purely by moving it through magnetic field lines. So we could either make the wire move through the magnetic field, or we could actually move the magnetic field in some way. So spin a magnet, anything like this will do the same thing. If the wire doesn't cut the field lines, then we will not induce a potential difference. Again, we have three ways that we can increase the induced potential difference. First, move the wire faster, cuts more field lines in any given moment of time. Secondly, we can use a stronger magnetic field. That means there are more field lines within the same area, so moving the wire in the same amount of space would create obviously a larger potential difference. Or thirdly, we could use more wire, generally more coils, and that means that in that same space of our magnetic field lines there'd be more times it's cut by the wire because there's more bits of wire there. Now, obviously, if that's all connected into our circuit, current will flow. And when current flows in a conductor, we generate a magnetic field. So what we then have is, if that wire is in a magnetic field, we will have a force acting on it. And that magnetic field that we're producing as a result of the current flowing is in the opposite direction to the field that produced the potential difference. So you've got that opposite effect. And this is always a good little trick that you can actually do. If you get a metal tube, so just any old metal bit of pipe, and you get a small magnet, then you can actually bet people they can't catch the magnet out the bottom. So you can demonstrate it with just a ball bearing that's not magnetic first of all, show them what it's like when it drops through. They'll kind of guess how quickly they need to then try and catch it. Do the same thing with a magnet, they'll miss every time. Because as that magnet falls through the actual pipe, what it's going to do is it's going to induce this potential difference, which is then going to cause a current to flow through it because it's a circuit, because it's a complete pipe. That then means we get a magnetic field produced in the pipe itself that's in the opposite direction to that being produced by the magnet. They oppose each other and your magnet falls nice and gently through the pipe. Therefore, you can win a bet every single time and make a bit of cash on the side. Now, the next bit is another device that we can use, which is an alternator. So in an alternator, the coil of wire is going to spin between the poles of a magnet. This is going to generate an alternating potential difference. And the reason it does that is because the potential difference changes direction, hence alternating. Now, the key difference here from our motor is, as opposed to our slip rings, then we are not going to be using our split ring commutator. We're using a slip ring this time. Now, what we actually find is that in this setup, there we go, got a picture of it here for you. There we are. So rather than the split rings, we have slip rings. So you can see there are two complete circles here. Now, what we actually find is that on the side we've got these carbon brushes, so that's not physically attached. They just rest against it and allow it to conduct through there. So because they're just resting but not actually connected physically, that means the coil will not tangle as it spins. The next device that we can have is a dynamo, and this is generating a direct current, or DC. So when we're looking at it, the alternator is AC, alternating current, and the dynamo is DC, direct current. So same first letter of the device as our current. The dynamo then produces a potential difference that does not change direction for the current. So what we end up with is a little picture, and I've lost my pen, here it is. So when we have a look to see what our current looks like, it's a bit of a dodgy drawing, but it gives you the idea, then it's always in the same region, it's always positive. So that means that we will not get a change in the direction. This uses a split ring commutator. So motors and dynamos, split ring, whereas our alternators, slip ring. Don't mix them up. Now, what we're going to find is the direction of our potential difference won't change because of the split ring commutator, for the same reasons as the motor spins. Because that gap obviously means it loses contact as it's at the 90 degrees, and the momentum keeps it going. When it reconnects, then what we find is that whatever bit of wire is on the right hand side of our device, the current is always flowing in the same direction. In terms of how we can increase the outputs of either alternators or dynamos, use a stronger magnetic field, use more turns on the coil, spin the coil faster. So we're seeing recurring themes throughout this topic on how we can actually increase outputs. Our next device is a transformer. Not the robots from the movies, nothing that exciting, I'm afraid. Instead, these are devices that either increase or decrease the potential difference. They are incredibly important to our ability to transmit electricity safely and not blow up our houses and factories. Now, what we actually find here is our transformer is then going to allow us to either increase the potential difference, particularly leaving power stations before it goes through power lines, or decrease the potential difference before it gets into our homes. Now, that's really important because we need it to be a nice high potential difference as it's being transmitted through power lines to minimise losses, but we don't want it to be tens of thousands of volts coming into our homes, into our sockets. Otherwise, someone sticking their fingers in a socket would end even more badly than it does when it's only 240 volts. So, what we actually find in terms of our transformers then is when we actually have a transformer, we've got something like this. So we've got a solid iron core, which you can see from that basically square of grey. That's our solid iron core. And then we've got two coils. You've got one coil on one side, the other coil on the other side. So what we have is a primary coil and a secondary coil. Now those coils are going to allow us to change the voltage. And the reason we can do that is based on the number of turns on the coils of the primary compared to the secondary. So we do know that when a current flows, it produces a magnetic field. When we're actually using our transformers then, what we see is that if the coil is turned on or off, we're then going to be changing the number of field lines cutting the second coil. Because of the setup here, in our primary coil on this side, this is connected into our circuit. So as it's actually having current flow through, it generates a magnetic field, which is obviously passed through the core here. Now, what we do know is that if we've got a magnetic field and we've got obviously our wire on the other side, then we can induce a potential difference there. So what we need to make sure of to actually make that happen is that this input is an alternating current, because that means it's constantly going to be changing between the positive and the negative, which means we have an alternating current. That means we're going to be getting a changing magnetic field, which means we're going to induce a potential difference in our other coil. So you've got to use AC for this. If you use DC, just doesn't work, full stop. Now, what we actually find then is when we're looking at the types of transformers, the ones that increase the potential difference are step-up transformers, and the ones that decrease the potential difference are step-down transformers. The way that a step-up transformer works, the one that increases potential difference, is it has more turns on the secondary coil compared to the primary. Whereas a step-down transformer, they have more turns on the primary coil than the secondary coil. So make sure you do know that. Step-up transformers increase the potential difference and they go up. So when you go from primary to secondary, you get more turns on the secondary. Whereas a step-down transformer decreases the potential difference, and that has the decrease in the number of coils as you go from primary to secondary. The last bit of the topic was looking at two more devices, loudspeakers and microphones. So we need to know how a microphone and how a loudspeaker works. And all it does is it brings these same concepts together again. If we think about the microphone, then what we actually have is our sound wave is a pressure wave. So hopefully we remember that basically sound is just all these particles in the air being kind of compressed closer together and then spacing out. So it's a pressure wave. As that pressure wave, that is our sound wave, travels through the air and it hits the diaphragm of a microphone, then what it actually does is it's going to push in that diaphragm. Where we've got a low pressure area, then the diaphragm will move back out again. So what we see is we get this kind of motion of in and out with the diaphragm based on the sound wave itself. So we have this kind of setup. Here's our sound wave. There's the diaphragm of our microphone. So any of the high pressure regions that hit it are going to push that in, whereas low pressure regions, it moves back out again. Now, as that diaphragm moves in, you can see it's attached onto this structure here, which is a coil of wire. And that coil of wire is sitting over a magnet. So as the diaphragm moves in, the coil also moves in, and because our wire is then cutting the field lines around our magnet, what happens is we generate a potential difference across the wire itself. That potential difference will then allow a current to flow because it's connected into a circuit. That goes off to whatever device our microphone is connected to, and the electrical signal is then transmitted through to make the sound on our computer, radio, whatever it may be. We do have another type of microphone, which is a carbon microphone, which basically, rather than having the setup there with the coil, instead it has carbon granules behind the diaphragm instead. So that as the sound wave hits the diaphragm, the resistance of our carbon will change, and then we will get a current passing through the carbon granules, and that current will change based on the level of resistance. The final thing is our loudspeaker, and the loudspeaker, quite simply, acts kind of like a motor, in all honesty. Because what we actually find is that we connect our wire onto a coil again, which sits over a magnet, and that's going to sit onto a diaphragm as well. So it's very similar to the microphone. When we have the changing potential difference passing through the wire itself, we get a changing current. That then produces a force on the coil of wire because that coil of wire is sitting in a magnetic field of the permanent magnet there. As a result of that, we then get the cone moving in and out, which produces the sound wave, because as that bit hits on the actual particles in the air, they get more compressed, and then as it moves away, they obviously space out a bit more, and that generates our sound wave. Obviously, the movement of the coil will depend on the size of the potential difference, so just bear that little bit in mind there. So that is all of P4 in a whistle-stop tour. Do remember the key things for this exam are right hand, thumbs up for just a single piece of wire. Left hand, Fleming's left-hand rule for our current carrying wire in a magnetic field in order to work out the direction. And this is going to work for the direction of motor spinning, anything like that. So the first thing you really need to understand before you can jump into how those devices work has to be Fleming's left-hand rule and the way that that actually moves wires within a magnetic field. Once you've got that, you can pretty much apply it to any of the different devices. So, hope that helps. Obviously, for those of you in my Year 11 class, you do have your test tomorrow. You will have your first physics lesson of the day just to do a little bit more revision, just because I'm feeling nice. And then we'll do second physics lesson, will be the actual assessment itself. Remember your calculator and brain cells, if possible, of course. Other than that, obviously go over any of the bits you're not 100% sure on, and I will see you tomorrow. Have a good evening.